Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper 4 exam for October-November 2019 variant 1. So let's get started. Question 1 says a car accelerates from rest at time t equals 0 to its maximum speed. Figure 1.1 is a speed time graph for the first 25 seconds of its motion. We have the graph straight line first, then curving and becoming horizontal. The mass of the car is 2,300 kilograms. For the time between t equals 0 and t equals 5 seconds, determine the acceleration of the car, and the acceleration on a speed time graph is equal to the gradient. So we need 2 points to find the gradient. We can use the first point 0 and 0 and then choose another point that makes a good intersection like this one. We have on the x-axis 5 and on the y-axis we have here 15. So we substitute here y2 minus y1, that's 15 minus 0 over x2 minus x1, that is 5 minus 0. And the answer will be 3.0 meters per second squared. Double I says calculate the resultant acting on the car. The resultant force here is equal to mass multiplied by acceleration. And we have the mass given in the question 2,300, then we multiply that by 3. We get a value of 6,900 newtons. Part B says describe the motion of the car between time t equal 10 seconds and 15 seconds. From 10 to 15 seconds we had a curve with decreasing gradient. So that would be a decreasing acceleration since gradient was positive and decreasing. And the positive gradient in this graph shows that the speed was increasing on the y-axis. Question C says between t equal 10 seconds and t equal 15 seconds, the force exerted on the car due to the engine, which is a forward force, remains constant. Suggest and explain why the car moves in the way shown by figure 1.1, decreasing acceleration. That can only be caused by a decreasing resultant force. But what decreases the resultant force if the forward force is still the same or constant? That is because as speed increases, air resistance increases, so the resultant force decreases and acceleration decreases. Question 2a says state two properties of an object that may be changed by the action of forces. We can say that the velocity might change. It may speed up or slow down or change direction. And we can also change the shape of the object by applying forces on it. Part B says a chest expander is a piece of equipment used by athletes in a gym. Figure 2.1 shows a chest expander that consists of 5 identical springs connected in parallel between two handles. Each spring has an unstretched length of 0.63 meters. Two athletes are stretching the chest expander by pulling on the two handles in opposite directions. I says the springs obey Hooke's law. Explain what is meant by this statement. We say that the force is proportional to the extension of the spring. Double I says each athlete pulls the handle towards himself with a force of 1,300 newtons. 1 says state the tension in each spring, and we have 5 springs, so the force will be divided by 5. So each one will have 260 newtons in it. Part 2 says the chest expander stretches and each spring is now 0.94 meters long. Calculate the spring constant of each spring. So spring constant is equal to force divided by extension. And we have the force 260 newtons. And the extension is the difference between the original length and the new length. So 0.94 minus 0.63. This gives an answer of 838.7097. So we can approximate that to approximately 840 newtons per meter. Triple I says state the energy changes taking place as the two athletes use their muscles to stretch the chest expander. So first from chemical energy stored in the athletes' bodies to kinetic energy, then to strain energy or elastic energy in the springs, since elastic energy is associated with the deformation. Question 3 says figure 3.1 shows a shooting competition where air rifles fire soft metal pellets at distant targets. When an air rifle is fired, it exerts an impulse of 0.019 Newton second on the pellet. Define impulse. We can say that it is equal to the change in momentum, or we say that it is equal to the force multiplied by the time over which the force was exerted. Part B says the pellet has a mass of 1.1 times 10 to the power negative 4 kilograms. Determine the speed with which the pellet leaves the rifle. And we have the impulse and the mass. We can use the first definition of the impulse. Impulse is equal to the change in momentum, which is equal to mass multiplied by the change in velocity. And we have the impulse 0.019, and we have the mass 1.1 times 10 to the power of negative 4. The final velocity is the required, and the initial velocity was 0. So we divide on the left side by 1.1 times 10 to the power of negative 4 to get the speed. The speed is equal to 172.7272 recurring. So we can approximate that to 173 meters per second, or 170 meters per second. Double I says the kinetic energy of the pellet as it leaves the rifle. We can calculate kinetic energy as half mv squared. M is the mass and v is the speed, calculated in the previous question. Half times 1.1 times 10 to the power of negative 4 multiplied by the speed, which was 173 squared. That gives an approximate value of 1.6409. We can further approximate that to 1.64 joules. Question C says the pellet melts when it strikes the target. Describe how the molecular structure of the liquid metal differs from that of the solid metal. We can say that molecules in solids are closely packed in long-range regular arrangement and vibrate about a fixed position, while in liquids, molecules are not arranged and exchange places. Or we can say that they slide over each other while vibrating. Question 4 says figure 4.1 shows a loudspeaker that is producing a sound wave in air of frequency 15,000 Hz. Describe how the cone of the loudspeaker produces this sound. We can say that as the cone vibrates forward and backwards, it makes the air molecules, or pushes the air molecules to vibrate, sending a series of compressions and rarefactions. And these compressions and rarefactions move through the air. Part B says the speed of sound in air is 330 meters per second. Calculate the wavelength of this sound. We have wavelength is equal to the speed divided by the frequency. Substituting, we have 330 divided by 15,000 Hertz. That gives an answer of 0.022 meter. Question C says the loudspeaker is placed a considerable distance to the left of a barrier with a gap. The width of the gap is double the wavelength of the sound, so it's a wide gap. Sound from the loudspeaker reaches the barrier and passes through the gap. Figure 4.1 shows the gap in the barrier. Now we are required to draw on the figure 4.2. We want to sketch a diagram that represents the sound wave as a series of wavefronts. So we have straight lines traveling towards the barrier, which means before the barrier, and in the gap, and traveling away from the barrier. Now when a wave passes through a gap in a barrier, it diffracts, but this gap is a wide gap, so it will not diffract by much. But just to make sure that we are drawing it correctly, we are going to use a ruler to draw in the direction of the wave. So I'm going to draw a straight line here. And we are going to mark equal distances. For example, we have this distance about 3 centimeters, so we are going to draw half of that. So from this point, we have 1.5, then 3, 4.5. So we have 3 wavefronts on the right of the barrier, and we have also 3 wavefronts on the left side of the barrier, before the barrier. Now we can draw the wavefronts. Now before exiting the barrier, the wavefronts are straight lines, equally spaced, which represents that the wavelength is constant, like this. And we draw the other 2 wavefronts, the last one here. And after the barrier, it is also straight line since the gap is wide, but with the same width of the gap. So the first wavefront will only reach the side of the gap here, and on the other side the same thing, and repeat for the other 2 wavefronts, like this and this. Now we draw slight curves on the ends of each wavefront. So we have a curvature on this side, a wider curvature on this side again, and we repeat for the bottom parts of the wavefronts, showing that the curvature increases, or the direction of the wave keeps spreading. And this is the direction of the wave. Question 5 says figure 5.1 shows a sphere that is negatively charged. The sphere is attached to a plastic stand. On figure 5.1, draw arrows to indicate the pattern and direction of the electric field in the region. So we can just draw straight lines pointing towards the sphere, arrows pointing towards the sphere, because the field around the negatively charged object is radially inwards. So we keep drawing arrows pointing towards the center of this circle, and this is the shape of the electric field. Part B says a smaller uncharged metal sphere S is suspended by a plastic thread. and brought close to the negatively charged sphere. Figure 5.2 shows the two spheres. Part I says by drawing on figure 5.2 indicate the distribution of charge on S, the smaller sphere. So the negative charge on the large sphere repels the electrons to the right and leaves the left hand side positively charged. Double I says state what happens to S now due to these charges. We say that it gets attracted to the large sphere because the distance between the opposite charges is less than the distance between the like charges. So the attraction between positive and negative is greater than the repulsion between negative and negative. Double I says an earth wire is then touched against S. Describe what happens in the wire and state how this affects the charge on S. Now for this whole system, it is more negative than positive. So when connected to Earth, the Earth absorbs the excess electrons. So we say here that electrons move from S to the Earth through the wire. And when S loses electrons, it becomes positively charged. So, and S becomes positively charged. And that's what happens with induction charging. If you bring positively charged object near a metal and then you connect the metal to earth and then disconnect it, it becomes positively charged. If you bring a positively charged object near a metal and then connect the metal to earth, it then becomes negatively charged. Question C says the metal sphere S is an electrical conductor. The plastic thread is an electrical insulator. Explain this difference by referring to the structures of the two materials. We say that metals have free electrons and allow flow of charge. And then we say plastic has no free electrons and does not allow flow of charge because the electrons are held in their atoms. Question 6 says figure 6.1 shows a shower that takes in cold water. The water passes through an electric water heater and emerges from the shower head at a higher temperature. The power of the heater is 9,000 watts. Part A says the shower is powered by a 230 volt electrical supply. Question I says calculate the current in the heater when it is switched on. So we can use current is equal to power divided by potential difference, or P equals VI. We have the power 9,000 and the voltage is 230. That gives an answer of 39.13. So it's 39 amperes approximately. Double I says state a suitable rating for the fuse in the heater circuit. We choose a value that is just above the calculated current, so we can use a 40 ampere fuse, for example. Part B says the specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. The initial temperature of the cold water is 16 degrees Celsius. Determine the maximum mass of water that can be heated to a temperature of 35 degrees Celsius in 1 second. So we can use the energy is equal to mc delta T, and we can replace the energy Q by power multiplied by time, and then we substitute mc delta T. Power was equal to 9,000 and the time here is 1 second in this question. The mass is the unknown, C is 4,200 joules per kilogram degrees Celsius, and the change in temperature is the difference between 35 and 16. So moving this whole part to the other side by division, we get a mass of 0.11278, so approximately 0.11 kilogram. Part C is about thermometers, which was removed from the syllabus, so you can skip this part. It says a safety control in the shower switches off the shower when the water becomes dangerously hot. The control uses a thermocouple thermometer to measure the temperature of the heated water. Part I says describe the structure of a thermocouple thermometer. Include a diagram in your answer. So we can only use the diagram since it includes everything. So we have voltmeter with two wires coming out of it. And at the ends of the wires, we connect these ends with another wire, and we call one side of these ends the cold junction, and this junction is immersed into pure melting ice. So we label that pure melting ice. And on the other side, we have the hot junction, and we label the wires. We have the wires coming out of the voltmeter must be made of the same material, so we say metal 1, or we can choose a metal, for example copper, and the other wire must be made from a different metal, so we say metal 2, or we choose a specific metal. If we choose copper, we for example can choose iron for the other wire or the third wire. And we can say that the voltmeter reading represents the difference in temperature between the two junctions. This is how the thermometer works. Double I says, suggest one reason why a thermocouple thermometer is suitable for this purpose. Since it is a response circuit, when the temperature gets too high, a switch closes the circuit or closes the heater or switches off the heater. We can say that a thermocouple has a quick or short response time. So it will switch off the water quickly before any damage happens to the skin. Question 7 says the resistance of a 1.0 meter length of resistance wire is 7.6 ohms. A length of this wire is taped to a meter rule. A crocodile clip is connected to one end of the resistance wire exactly at the 0 mark of the rule. Figure 7.1 shows the crocodile clip connected to terminal P, which is open for now. The second terminal Q is connected to a movable contact using a long length of connecting wire. The movable contact is in contact with the resistance wire at a length L from the 0 mark on the rule. So we use different length of wire in the circuit. Question A says on figure 7.2 below, sketch a graph to show how resistance R varies with length L for values between L equals 0 and L equal 1 meter. Mark appropriate values on the axes on the graph. And we know that resistance is directly proportional to length. So the graph will be a straight line through the origin. And the end of the line is at 1 meter for the length and at the maximum resistance of the wire on the y-axis. The maximum resistance here was 7.6 and the maximum length was 1.0 meters on the x-axis. Part B says figure 7.3 shows a battery of electromotive force 12 volts connected across the 1.0 meter length of the resistance wire. Part I says state what is meant by electromotive force or EMF. It is the energy needed or supplied by the power supply or a battery if there is a battery to a unit charge to move across a complete circuit. Double I says calculate the current in the resistance wire. We can use current is equal to voltage divided by resistance. We have the voltage 12 or the EMF 12 and dividing that by the resistance of the wire 7.6. That gives an answer of 1.578947, which we can approximate to 1.6 amperes. Part 2 says calculate the potential difference between terminals P and Q for a length of 0.35 meters. So we say if 12 volts are given to the total length of 1.0 meter, how many volts are given to 0.35 meters? We can use cross multiplication since voltage is proportional to resistance and resistance is proportional to length. So voltage is proportional to length. So using cross multiplication, we multiply 12 by 0.35 dividing by 1. That gives an answer of 4.2 volts. Part 3 says calculate the charge that passes through the resistance wire in 5.5 minutes. We use charge is equal to current multiplied by time, and the current was equal to 1.6. Multiplying that by 5.5, then converting from minutes to seconds, we multiply by 60. That gives a value of 528 coulombs, so approximately 530 coulombs. Question 8 says figure 8.1 shows a ray of red light incident on one side of a glass prism in air. For red light, the refractive index of glass is nr and the angle of incidence is 53 degrees and the angle of refraction in the glass is 30 degrees. Calculate nr, which is the refractive index. It is equal to sine the angle in air divided by the angle in the medium, or sine the angle in the medium. So we divide sine the angle 53 over sine the angle 30. That gives an answer of 1.59727, which we can approximate to 1.6, and the refractive index has no units because it is a ratio. Double I says on figure 8.1, sketch a line to indicate the path of the red light when it emerges from the glass prism and label this path R. So from this point, it does not go straight, it bends away from the normal, so it bends in this direction. So this is the direction of the ray, and we label this ray R. Because the normal here is like this, perpendicular to the surface of the prism. Also, we have another normal here for the incident ray, so we say that the red light moved away from the normal. Part I says explain why the quantity refractive index does not have a unit. We say because it is a ratio of identical quantities. For example, if you have meter divided by meter, then they cancel out each other. Part B says for violet light, the refractive index NV of the glass is slightly larger than NR. A ray of violet light is incident on the prism along the same path as a ray of red light. On figure 8.1, sketch a line to indicate the path of the violet light in the prism and when it emerges into the air. Label this path V. So for a refractive index greater than the original, it bends more than the original. So going into the glass, it bends more towards the normal. So going towards this line, towards the normal, but not by much. And now we have another normal here, and we say that it will also bend away from the normal. So it will not continue in the same line. It will bend away from the normal, but with a larger angle, because the angle of incidence here is greater than here. So this is the new ray, and this is V. Part double I says when a ray of white light is incident on the prism, dispersion produces a continuous spectrum of colored light. State how the speed of the light in glass depends on its frequency, and explain how this is shown by the dispersion of white light in the prism. So violet has a higher frequency and it bends more in glass, so it slows more in glass. This means that as frequency increases, speed decreases for electromagnetic waves inside the glass. Question 9a says the chemical symbol for the element lithium is Li. The proton number of lithium is 3. Figure 9.1 is a representation of a nucleus of a radioactive isotope of lithium that is about to decay. Write down using nuclide notation the symbol that represents this isotope of lithium. So these circles represent the nucleons, and we have 8 nucleons. So lithium has a nucleon number 8, and the proton number was already given as 3. So the dark or the striped circles are protons and the white circles are neutrons. So we have 5 neutrons. Double I says this isotope of lithium decays by beta particle emission to form another nucleus. Complete figure 9.2 below to represent this decay by using the same representation as in figure 9.1, which means using the circles, and in the space after the arrow draw a diagram of the nucleus formed by the beta decay, and by writing the name of the particle that is identical to a beta particle on the answer line provided, that would be an electron. And using the circles, the proton number increases and the nucleon number decreases. The proton number increases by 1 and the number of neutrons decreases by 1. So for example, we have 4 protons now, and they are still a total of 8 particles, and we have 4 striped circles and 4 white circles now for 4 protons and 5 minus 1 for neutrons. Part B says a radiation detector is set up in a laboratory where there are no radioactive samples. On 6 separate occasions, the detector is switched on for 1 minute and the background count is recorded. The counts are 23, 27, 25, 24, 20, and 25. State why the readings are not all identical. That is because background radiation is random, or a random process. Double I says suggest a possible source of this background radiation. We can say radioactive gases in the atmosphere, or rocks underground, or we can say there are cosmic rays coming from outside the planet, or due to living organisms emitting radiation, that would be beta particles. So any source of background radiation. Part triple I says a sample containing only one radioactive isotope is brought into the laboratory. The half-life of this isotope is 15 hours. This sample is placed near to the radiation detector in the laboratory. The detector is switched on, and after 1 minute a count of 440 is recorded. The sample is left next to the detector and the experiment is repeated. 45 hours later, the detector is switched on for 1 minute. Predict the reading on the counter obtained in this occasion. First, we need to calculate an average value for the background. We have the values from the previous page: 23, 27, 25, 24, 20, and 25. We add these all together and then we divide by the number of the readings, which is 6. That gives an average of 24. Then we use that to correct the initial reading, 440 minus 24. That gives an activity of 416. This is the initial value. Also, we have the total time of the experiment and the half-life. So we divide the total time by the half-life to know how many half-lives are there. We have 3 half-lives, so we divide by 2 3 times. Then we take this value, we divide it by 2 to get 208, divided by 2 again. This is the second time, 104. And the third and last time we get 52. Then we add the background to 52, so we add 24. That gives a final answer of 76 counts. So this was the end of the exam. I hope you enjoyed this video and found it useful. If you liked it, give it a thumbs up and subscribe to the channel, and I will see you in another video.